déplaces tout, c'est mieux pour faire un clone de l'image. C'est votre celui.
Attends, je vais brancher ceci. Si, il y en a ici.
Ah, si, il y en a ici.
Il y a un PC.
Je vais te mettre le pointeur. Je vois si tu veux aussi, ça va le pointeur.
Ok.
C'est faire un clone, ça se fait sur ça.
Oui, attends, hein, encore ceci. Je me suis vraiment laissé embobiner par... Voilà.
C'est vrai, non, ça n'est pas montré parce qu'il faut cloner son image. You know, to make a clone? To make what? A clone on a Mac. Because it's
System
preferences.
preferences.
Clone of the control F5 is not the same as the. I think it's in the app settings and then display.
Display.
Yeah. And then tu me reviens play. Yeah. Got a window. Ah, it's on the other side. Mirror display. Là.
Mirror display.
Ouais.
Yes.
Xavier, I saw
Yes. Yes.
There is a PDF. If I can get a PDF from Matteo,
Did Matteo send
me? So I will just need to. Wait, and you know, we also send sorry, you also send the one from you said the one from one of the or these are one you do. Yeah, we do the I can do it now. I will just forward the material email. So this is right now. So I forward to okay, so I send this and so we can print them out and then yeah, you can also send already to the 1.1. So hopefully you get I hope you got the PDF with that forward.
Voilà, et puis je vais te le mettre. Voilà, j'ai déjà quelques minutes de retard, mais bon. Voilà, tu dans ta poche. Oui. Et normalement, tu peux utiliser de. Ouh, fantastique. Okay, so let's start with this introduction to ABINIT that is needed for this hands-on session of this afternoon. So a quick historical background. The ABINIT project started in '97 at the time where it was already clear that the potentialities of density functional theory and first principle calculation was so huge that one could not simply keep software code in one group, but one needed a collaboration. And at that time, we had a very nice model, the Linux software, which was delivered under the a license, a free license. And now we have a large number of people registered on the forum. ABINIT is 900,000 lines of Fortran 90, and this is more recent, many Python scripts. There have been 50 contributors to ABINIT version 8, and you will be using the very last unofficial version 8.76 in this school. So some milestone, we released for the first time the ABINIT in 2000, but it had already some precursor, the Corning plane wave code. And then every 2 years, we have a developer workshop between 35 and 60 participants each. Yes, here's a picture. So ABINIT, I would say, is a state-of-the-art, robust, flexible, and free software. This will be my first section. Then I will show some basics. I know that perhaps many of you are already familiarized with ABINIT. In any case, you are familiarized with Quantum-Espresso these days, and the two codes are quite similar in their basics. Still, kind of, it's good to explain the basics for those people who are not familiarized with ABINIT. I will spend some time showing how to go beyond the basic, looking at the documentation. And then I will introduce the density functional perturbation theory and the Electron-Phonon lessons of this afternoon. And I will finish with some perhaps advertisement of the interesting things that one can do with the Python script that we have developed recently, ABINIT Phonon Dance Structure on the Material Project website. So you know that indeed the capabilities of first principle code is huge, with the capability to go in particular to vibrational properties, but also optical response, perconductivity, etc. So, like Quantum-Espresso, ABINIT has many capabilities. I will quickly go through them. We can do calculation using the most simple basis set to do electronic structure calculation, namely plane waves with norm-conserving pseudopotential. But we also have the projector augmented wave for many, but not all, capabilities. It's more difficult to develop than with norm-conserving pseudopotentials. And we have many pseudopotential types that can be used, and also different PAW generators. At the level of density functional, LDA, GGA, many, we are using the libxc library as many other codes, LDA plus U, GGA plus U, hybrid functionals, as well as some advanced functionals, linear response time-dependent density functional theory, but for finite system only, GW for accurate electronic energies, and there also one can have very many flavors of GW, Bethe-Salpeter to get the accurate optical spectrum, and dynamical mean field theory, which is a bit of a semi-empirical in the sense that there is one parameter that is not completely a first principle to be used for such calculation, but this theory is very nice for strongly correlated materials, like strontium vanadate, for example. Of course, insulator metals, collinear spin, non-collinear spin, spin-orbit coupling, and optimization of the geometry, molecular dynamics, path integral, molecular dynamics, determination of saddle points, everything is coded indeed. One can compute susceptibility metrics by sum over state, optical spectral by sum over state, but also by some other way, Bethe-Salpeter. Polarization and finite electric field calculations are possible. Yes, finite electric field calculation is the going beyond the very phase implementation of the polarization. One can do molecular dynamics under a finite electric field, for example. Electric field gradients, positron lifetime. We have, I think, a nice symmetry analyzer, including the Shubnikov magnetic group. Okay, one strength of ABINIT, which is also a strength in Quantum-Espresso, of course, is density functional perturbation theory. Responses to atomic displacement, static homogeneous electric field, but also, and this is quite unique for ABINIT, to strain perturbations, and very recently to magnetic field perturbation in the Zeeman sense, and the part of the magnetic field that couples to the spin. And that is, for example, very important, the dominant term in magnetoelectric coupling, usually. These give access to a lot of second-order derivatives of the energy. I will not go through these, but also to the temperature dependence of the electronic structure. So, I mentioned that ABINIT was quite robust and well tested. We have a test farm and a test suite, more than 1,000 automatic tests. And this is quite nice because we are also testing the input and output of the tutorials that we provide. So we are sure that at any time we have working input file and output files and corresponding output files for our tutorials. Actually, we introduced, well, the software BuildBot, we pioneered its usage in computational condensed matter. Switching to the Python capabilities, this is actually not shipped with the usual ABINIT package because it needed quite, well, several years to be developed, and we didn't want to have people worrying about what was appearing and that we were not describing. So actually we have an ABINIT organization on GitHub, and on this, this is a snapshot of this GitHub web page. You have here a mirror of the official ABINIT size, but you have also here ABIPy, the Python script for ABINIT, and here ABITutorial. And on this GitHub page, you have many, many other projects that belong to the ABINIT GitHub organization. What is ABIPy? It's a library for launching ABINIT jobs and analyzing, plotting the results. Launching ABINIT jobs, there are many scripts that are flows that will drive very complex calculation in ABINIT. ABINIT has some flow capability in itself that I will detail later, but of course with Python script you can do many, many more things than simply what can afford the native capabilities of ABINIT. And analyzing, plotting the result is also very nice because within the standard ABINIT, we provide files, and then we say to the user, well, use XMGrace or you use GNUplot. But here with ABIPy, we link to Matplotlib, and there are many, many visualization scripts that are already prepared and that then can be used, just downloaded from the web to do your visualization. And we have also ABITutorials. They are based on Jupyter Notebook, ABINIT plus Python. At this stage, perhaps half of you do not know what I'm speaking about. I hope the other half know what I'm speaking about. And don't be afraid because we have, for this afternoon, 2 tracks. Those who do not know about Python and Jupyter Notebooks will follow the conventional path for the tutorial of ABINIT. The others might actually choose another track in which we will have these ABIPy, ABITutorial exposed. Okay, so like Quantum-Espresso and some other code in the academic community, we have a free license, the GPL, General Public License, that gives you a lot of freedom, unlimited use for any purpose. You can study and modify for your needs. You can copy and even distribute modification. So if you're interested to know exactly what is it about this licensing scheme, we can discuss afterwards. So, and in this website, you can have the download and the documentation. A few references. So everything is on the website of the school. So I will. Okay, so running ABINIT, some basics. This is a mental model of what is ABINIT, I would say. There is a parser of an input file that immediately is followed by some checks, prediction of memory needs, etc., and then passes the information to a driver. The driver can address different processing units, let's call it, among which this big one everything, well, a lot of things that are DFT-based, except the density functional perturbation theory is there. Density functional perturbation theory is here. Then there is a processing unit that goes to the nonlinear responses using the 2n+1 theorem. Processing unit GW, Bethe-Salpeter, and very recently we have developed a specific processing unit for electron-phonon properties. And actually, in an input file of ABINIT, you not only specify one kind of job to be done, but it's possible, because of its managing flow capability, to say, I would like to start to make a relaxation, and then take the output to start a density functional perturbation calculation for many different phonons, many different Q points, and then I will go to, GW computation of the band structure, and perhaps finish with the optical property of the material. It's possible to make a very complicated then input file, but you know, the geometrical part is often the same. It's just E-cut, number of atoms, pseudopotential, etc., and you might fix your cutoff energy and do the whole chain. But you can also, in one ABINIT run, simply make a convergence study, starting with a relaxation at 5 Hartree cutoff, then going to 10, 15, 20, etc. So this is indeed possible. So, taking ABINIT as this item, ABINIT must first receive the names of the files that he has to work with. And in this file names file, he will find the name of the main input, the name of the pseudopotentials, perhaps the name of previous results that might help to restart. And it will produce a log file, you know, very cumbersome, so not very interesting in general, except if you have errors. The main output, which is more human-friendly, and then other results. These results and these two results might be, beyond the log and main output, energy derivative, what we called derivative database in ABINIT, so second derivative of the total energy with respect to atomic displacement that will give the dynamical matrix, after all. These are a whole set of text files, and then there are also results like density files, wave function files, potential files, perhaps third-order derivative of potential, first-order derivative of wave function, etc. That might be binary Fortran files, but you know that's not a very good format, even if it's very compact. You cannot take such a file and use it on another computer. Very recently, well, it has been already some years, but it's developing, we have the capability to output netcdf files that are perfectly transferable and also can be addressed by content instead of having to be read linearly. So netcdf files are very Python friendly. And okay, I like to insist on this capability of ABINIT. So this is a basic file, the one that delivers file names. And I will take the example here of simple H2, the dimer of hydrogen. The first name here will be the name of the input file. You see, the name of this main input. The second name will be the name of the main output file. Okay? And then I cannot specify all the file names. I have tons of such files. What we have chosen to do is to use root name for possibly all other input files. That will be H2I. Then it will be appended with underscore DEN for density files, or underscore pot for pot files, etc. Same thing for the output files, and we have also a location for temporary files. Of course, these things might be located in possibly different directories. That's not a problem. You simply are given quite a large capability to manipulate your other files. And then we need the names of the pseudopotential files. Here I have said hydrogen with this name. It's the file that I will need for doing my hydrogen calculation. But suppose that we also need oxygen and uranium. I will add another name and then a third name. So one file needs 6 lines, at least. Perhaps it will be 7 when there are 2 types of atoms, 8 if there are 3 types of atoms. As mentioned, we have indeed pseudopotential table. This is an example taken from the website of ABINIT, the GTH table that has been thoroughly tested and used in many calculations. So it is quite safe. And this is, for the non-conserving case, the so-called pseudo-dojo table that is a very recent product, and that has some nice feature. For example, you can perfectly download something in different formats. So there are some formats that ABINIT like, but you can produce the UPF format that is more used for Quantum-Espresso. Okay, so it's a very recent paper. And we have LDA, GGA, PBE, SOL potentials available, all thoroughly tested. Okay, now we come to the input file. So this will be for H2 molecule in a big cubic box. Just to tell you, characters after this sign or after this one are comments and will be ignored by the parser of ABINIT. The basic idea is that one has a keyword followed by values. And the order of keywords in the file is not very important. You can group them. You can group because you would like to have this combination of input variables. Or you would like to single out that this input variable is very important because it's the one that you will want to modify later, etc. Up to you. Definition of the unit cell keyword is a cell, and it is followed by 3 numbers, 10 by 10 by 10. It is a 10 by 10 by 10 cubic box in atomic unit, Bohr. Okay? If you want to use angstrom or nanometers, no problem. ABINIT can identify these, but you have to add here nanometer or angstrom. By default, it's always atomic unit. Okay? Definition of the atom types. Well, we have hydrogen, so only one atom type. N-type at is 1. What is the nucleus charge? It's 1. So we specify these. Having defined the atom types, we can specify the atoms themselves. We have 2 atoms and atom 2, each of type 1. If I had barium titanate, I would have 3 types, 1, 2, 3, and here I might have found 5 atoms, then 1, 2, 3, 3, 3 for the 3 oxygens. And then a starting position for the atoms. It's a simple dimer, so -6 and +x position, and then 0, 0 for the y and z coordinates. Nothing fancy. It is given again in Bohr. If you like angstrom, you can put angstrom, like for the unit cell. Now come the definition of plane wave basis, convergence, k-point grid, etc. E-cut is equal to 10. It's, I think, the same in Quantum-Espresso, if I'm not mistaken. Yes. Definition of k-point grid here, because we are working in a big box, it's only one k-point that will be gamma. Later, I will show you more, well, what are the possibilities in ABINIT to specify the number of k-points, etc. And then definition of the self-consistent field procedure, a maximum number of steps, a tolerance where if you have reached this tolerance, you simply stop. You don't go to the total final number of steps. And then it's not mandatory, but to help ABINIT to do the SCF convergence can prove useful in some cases. This is the macroscopic dielectric constant for a big box with only one atom. It might have been 1. It's simply a helper to possibly speed up the calculation. Then in the tutorial, we'll find that all input files have some added information after this double sign. These are metadata for the automatic testing. So do not worry about this. You should not have a look at this. But it's also including a description of the test. So this might be useful nevertheless. Okay. There are some input variable flexibility. Let me illustrate this for the specification of the geometry. Of course, the primitive cell might not be a cubic one. By default, it is a cubic one, but one can perfectly specify the primitive vectors thanks to this input variable, or the angles between the primitive vector. This is another possibility. And one can rescale these initial primitive vector either by length or by scaling the Cartesian coordinate. Will become clear later. The atomic position can be specified in radius coordinate as well as in Cartesian coordinate. And the level of the symmetry of the system that I will also show quickly, we have also different possibilities. We could specify the space group plus the number of atoms in the reducible part of the zone. ABINIT will reconstruct the full set of atoms, or on the contrary, we might give the full set of atoms, and ABINIT will deduce the number of symmetries and the symmetry operation. An example for cubic zirconium dioxide that is FCC with 3 atoms per unit cell, 1 zirconium and 2 oxygen. One possibility to specify this is N atom 3. Then the A cell, it is the length in angstrom here. And then you see here comes the first meta character in the input file of ABINIT, a star, which is preceded by a repeater. Okay, so 3 star, that value is equal to value, value, value. Okay, and sometimes I have to specify 100 very similar values. It is very easy to do thanks to this trick. And in this example, I specify by hand the position of the 3 atoms, which means that the symmetries will be found automatically. But another possibility, the lines here are exactly the same, is to specify the space group, the number of atoms to be read, and only give the position of 2 atoms. Of course, for such a simple case, it's kind of obvious, but when you have, I don't know, a zeolite that might be very symmetric, might be good to have this possibility and still have to specify 50 atoms. Oh, you can also download a file from the materials project, UCSD, etc., and ABINIT will be able to read and input the corresponding Cartesian coordinate. Yes, here I wanted to mention the use of angdeg, which gives the degree, the angles in degree to specify, for example, the trigonal unit cell, and also to illustrate the scale card versus A cell capability of ABINIT. But let's say that's not really very interesting. This is the way we handle the symmetries. It must be very similar to other codes. SymRel is the 3x3 matrix that gives the point transformation, and then there is a translation that has the keyword T-nonce. Yes?
I would like to know if the algorithm that find the symmetries in ABINIT and find, for example, center of inversion, if it is not exactly at the center of the state. For example, if I translate my crystal by
yes.
we find it.
Yes.
Yes.
Yeah.
And how is it possible to deal with the inversion center, for example, in the Boolean zone, if it is not inversion center of the unit but of the
yes, then in the Brillouin zone, the inversion will be also associated to a phase change. That's the way.
I don't care how I set my symmetry, how I reach that I just make it flat, it will always make the symmetry and be used.
In principle, yes. There is some small correction to it, because for GW calculation, not all non-symmetric symmetries will be treated by the GW algorithm, or perhaps you have this. Okay, so sorry for at some point it was not possible, but now it is treated. We might discuss this further, of course, if you want. Okay, plane wave basis set is the same as in Quantum-Espresso, E-cut input variable. So I will also quite go quickly on this slide. K-point sampling needs a bit more because you will have to deal a bit with K-point sampling in the tutorial. So, of course, the Monte-Carlo grid is the standard in many code, and we have this capability. We have something also more powerful, but a bit more delicate to use. So let me explain the Monte-Carlo grid. It will be associated with the NJ-KPT input variable. You give 3 numbers, and it will be the sampling along the first reduced primitive vector, and the second one, and the third reduced primitive vector. So in this 2-dimensional case, you get this grid for 3 here and 3 there. And if you put 4, you get a 4 by 4 grid. But of course, these are centered grids in which the first point of the grid is located at the origin of the Brillouin zone. But it's also perfectly possible to shift the grid in order to try to minimize the number of K-points in the irreducible part of the Brillouin zone for materials that are very symmetric, and when the number of K-points is not very large, it might allow to save a significant amount of computing time. This is associated with the shift K value, which is a set of 3 input, 3 real numbers. The default actually in ABINIT is 0.5, 0.5, 0.5, which means that we prefer to use a shifted grid by default. But one can also actually combine different K-point grids still in an homogeneous way, like this one, because again, it might have some advantage compared to a standard Monte-Carlo and PAC grid. And I don't show you the most powerful thing, but it's too complicated. So why are we interested with this K-point grid to be kind of have a nice properties? Is because for ground state calculation, we have to sample only the irreducible Brillouin zone wedge. Thanks to the symmetries, we will reconstruct the density or all quantities that belong to other parts of the Brillouin zone. But it is the case when you can use, indeed, the symmetries to reduce it. With phonon and electron-phonon, you very quickly, for example, start with some wave vector of the phonon, and then the calculation must preserve this wave vector of the phonon. So one cannot use the full set of symmetries of the original ground state problem. One has to go to the little group of symmetry of this wave vector. Finally, to finish this basics tour in ABINIT input variable, one has to specify the input variable linked to the algorithms themselves, which mean how to solve the Quantum equation. Usually these details are hidden to the user. Oh yes, of course, there are many default values that you might completely get to ignore in ABINIT. And for example, the number of line minimization in this Quantum equation, you usually never touch, as well as the tolerance. Here, many users will ignore this. The self-consistency, on the contrary, is more important. I have already mentioned the number of steps for ABINIT, and there are different tolerance criterion to decide to stop the self-consistency loop before having reached the maximum number of loops. And there are also some preconditioners to speed up the calculation, but they are, let's say, not very important. And the geometry optimization and molecular dynamics will rely also on some input variables. The maximum number of loops or time step is n time. The algorithm is governed by ion move, and there is also some tolerance to decide where you consider you are converged with respect to the force that are still present, or respect to the stresses that are still present. Okay, sorry, I have not yet finished. This will be also important. It is possible to do non-self-consistent calculation in which you don't want to obtain a density at the end, but you consider that you have already done the self-consistent work, you have obtained density, you have obtained a potential, and you want simply to obtain a very large number of eigenenergies along different lines in the Brillouin zone. It is possible indeed then to start from a potential file and simply solve the Schrödinger equation. This corresponds to this input variable with that value, -2. And the path is specified by a number for this option. The points there and they are specified by this quantity, and the number of divisions along each segment is specified by that quantity. At that stage, you must say, how is it possible to remind all these input variables? And I have to go beyond the basics to show you that's not so difficult. Actually, we have a central documentation in ABINIT that is available on the website. Actually, it has a separate address, but you click on the portal of ABINIT and you will quickly find the link to go to the documentation, where we have a user guide, well, many users guides and installation notes. This is a snapshot of the homepage of the doc. So if you can look, you will be given the opportunity during the tutorial. User guide, there is a user guide for the main ABINIT, but also for many helpers. The manipulators of the files have their own guide. There is something for optic, for space group, fold 2 block, the unfolding of the electronic structure. Okay, I do not have to describe this here. Installation is described here. And then in this header, I had here the file the screen corresponding to user guide, but then we have a list of topics. Topics are small web pages in which we have tried to survey all the capabilities of ABINIT by a short introduction, and then it's kind of a hub with a set of related tutorials, a set of related input variables, and possibly also bibliographical references. And we have 70 topics like this that are very convenient. If you don't know what is the name of this input variable, but you know that you would like to do that thing, find the corresponding topics and look at the resources that are available there. The input variables are indeed centralized, and it's very easy, I will show you, to navigate through them. All lessons of the tutorial, you will be exposed to 3 lessons of this tutorial. We have 30 lessons that are available. Theory documents include the bibliography, and also we have more than 1,000 example input files, as well as, in the case of tutorial, the reference output. We have also things related to the Python, galleries, actually, for the plots and for the flows. Let's try to see this. You can download short scripts that can show you how to compute the Eliashberg function the MGB2 Fermi surveys, Bruneian parameters, projected phonon DOS very transparently. And at the level of the flows, is of course a more abstract quantity, but that you can represent by the tasks that are called by the central script. And the flow for phonon with DFPT is represented by this, while the flow to analyze the convergence of phonon in metals with respect to the sampling of K-points and the smearing is represented by this figure. Okay, at this stage, yeah, I will still show you this before making an example. So the ABI tutorial is based, well, the website is here, is based on Jupyter Notebook. Very fast execution of the tutorial, so you can simply read and you make a click, you execute ABINIT. You can continue to read, you make another click, you execute ABINIT, and possibly some other executable. It's quite recent, we only have 7 lessons available there, but we have developed for the present school the DFPT and the Electron-Phonon ABI tutorial. The list of what is available here is presented, the H2 molecule, very simple, crystalline silicon, and then phonon, dielectric tensor, and bond effective charges from DFPT, G0W band structure, Bethe-Salpeter equation, and excitonic effect, and then electron-phonon self-energy and temperature-dependent band structure, and phonon line width and Eliashberg function of aluminum. Let's go to a small demo, if I can. It's always risky, but I hope it will work. Yes. So this is the main page of the ABINIT documentation. And here, if I want, for example, to know what is this reference to Payne, Tether, Alan, etc. that's mentioned, you see you have the title of this reference, and if you click, you go to the bibliography central repository of ABINIT with the description, the reference, the DOI, and also the BibTeX. If you want, oops, I click here, I have the BibTeX that you can simply copy, paste in your paper. So let's go back. The topics, as I mentioned, 70 different, it's in this column, the list of topics. Some are Coulomb, crystal, DFT plus U, density potential, DMFT, electronic band structure. For all these small keywords, you have a hub, and also they are arranged in some sections like settings for atoms. This is the very basic. Physical settings for electrons, exchange correlation functionals, etc. Numerical settings. So this is for the topics part. The variables. As I mentioned, there is a whole set of ABINIT variables, so we have set up a search tool. If you're interested in ECUT, I start with ECUT. For example, having typed only ECU, give all the input variables that have this string ECU inside them. So I can click here to ECUT. Yes, and oh no, it didn't work. Why didn't it work? ECUT. Yes, okay, it worked this time. So for each variable, there is actually the mention of which topics mention this variable, and also here statistics of its usage. Is it an important input variable? Well, it's used actually in the 973 tests of over 973 tests of ABINIT. So it's a very important input variable. and I can click, oops, and I get this list of tests, but only a subset, the one that are used in the tutorial, and I can click on the this input file and find an example of usage of this input variable. Okay, finally, I will switch now to the lessons. The welcome page for the lessons is the following. The 4 basic lessons are advised to every beginner with ABINIT. And then they open up the possibility to do a whole set of other tutorials, like full 2-block, Vanilla 90, etc. But also this set of lessons, DFPT1, optic, DFPT2, L-phon, and the temperature of the electronic structure, you will be doing this one, that one, and that one. There are also tutorials for the parallelism inside of ABINIT. Okay, now I would like to come back to my main presentation. Yes, it's working. So this I have already shown. Then, of course, the goal is temperature dependence of the electronic structure. But we have to do something because it's not possible to follow the really needed tutorial. This would be, let's say, for newcomers, 10 to 15 hours of work. So what we have decided to do with these 3 hours is to bypass the 4 basic lessons and to suggest you to focus on the FPT response function 1 and response function 2, plus this temperature dependence of electronic structure. And of course, what you don't understand, you simply skip. Okay, or perhaps call us Matteo. Samuel will also help, and this will be fine. You will do the tutorial by looking at ABINIT documentation webpage, because everything is available on the web. So it's a paperless tutorial that we will have here. But this track is one possibility. The other track is with ABIT tutorial, the Jupyter Notebook base, that I will also show a bit more in detail later. In the first track, you will be computing this phonon band structure, and then this temperature dependence of the electronic value, I think, of the top of the valence band of diamond, if I'm not mistaken. And then at the end, you will be shown how to compute this thing, as though you will not perform such a nicely converged calculation. This was obtained with a 43 by 43 by 43 Q-point grid, so a bit hard. In the ABIT tutorial track, more things are visualized because this matplotlib capability of Python script. But the problem is installation of ABINIT running in conjunction with ABIPy. Well, you will be shown, if you really want to do this, how to make it indeed. So introducing now DFPT and Electron-Phonon lesson specifically. I have shown you this equation, the 0-point motion change in eigenenergy that is coming from the electron-phonon coupling energy, and I have suppressed the Bose-Einstein factor here and simply kept the 1/2 that corresponds to temperature equal to 0. And this quantity, I take here the fan contribution, comes from things that are in blue and things that are in violet. This comes from the phonon eigenmodes, and these, well, it's a mix of quantity that come from phonon calculation. The first order change of Hamiltonian comes from the first order change of potential, but also one encounters these wave functions of the ground state. Okay. Actually, using the Steinheimer trick, one part of this expression can be rewritten as just the first order change of wave function due to a specific perturbation. So we will need several files. We will take them from unperturbed ground state calculations, typically the eigenenergies, those that are, for example, here, and wave functions at k and k plus q with this label, and also from Phonon DFPT calculations with vector q, energy derivative, the derivative database file that contains the second order derivative of total energy with respect to atomic displacement, but also Electron-Phonon matrix element. This is the so-called GKK file that is written in NetCDF that can be looked at, and you can actually work directly with these matrix elements generated by ABINIT if you are interested to develop your own capabilities. First order wave functions with this label 1WF, and then the X here I will explain you later what is it about. And then there is also some file for the second derivative of eigenenergy, the factor in blue. This factor, the real part is eig R2D.NC, and the imaginary part is eig I2D I, with an I here. Real part, it corresponds to real part of the self-energy and imaginary part of the self-energy. The flow for a phonon calculation can be represented by this graph, self-consistent ground state calculation, and then one prepares the wave function at shifted k plus q value. This is represented here, and then one can start to do the real DFPT calculations. But one has also to compute, usually for insulators, well, polar insulator, the Born effective charges and the dielectric constant. This is done by these blue boxes. First, what is called derivative with respect to k, which is similar to applying the R operator, the linear potential operator. And then in yellow, it's hard to see, but it's the response with respect to an electric field. All these tasks generate a lot of files. It actually might be very interesting to just launch them on separate CPUs, and so it's very parallelizable, but needs to be gathered. This is done by merged derivative database. And final, this box is analysis of derivative database, ANA-DDB. So these are post-processes of the main ABINIT. And for the Electron-Phonon, this is a simplified flow. You might have in, well, there are two different possibilities. Actually, we are just in a transition period. There will be some common ABINIT calculations, and then one extracts the Electron-Phonon matrix element and one uses a post-processing Python script. This has been developed by Samuel, actually, and will be discovered using the conventional tutorial. But actually, we have also decided, because we needed in some case to do a lot of calculations, to redevelop this in Fortran. And this is then included in ABINIT using this input variable. This will be shown in the ABIT tutorial, and the flow is the following. We are doing a lot of phonon calculation. We also take into account the eigenvalues, eigenenergies, eigenwave functions in different cases. We merge the thing and then re-enter the ABINIT with the Electron-Phonon module, the module of the driver. And now, some input variable. In ABINIT, the DFPT is implemented by considering perturbation in which one atom is moved along one real space direction. If I understand correctly, in Quantum-Espresso, Quantum-Espresso work with symmetrized set of atomic displacement. Not a Quantum-Espresso expert, but here we really compute the derivative of quantities with respect to one atomic displacement. The number of the atom whose position is perturbed will be denoted by I_PERT. Of course, the maximum value is an atom. And the direction in which this moves is I_dir, 1, 2, 3 for the 3 primitive vector directions. And then we assign to all these perturbations one number in the set of 3 times n atom possible perturbations for one Q point. This gives the name PERT case, 3 times I_PERT minus 1 plus I_dir could run from 1 to, sorry, it's 3 times n atom here. Sorry for the error. And then we have an input variable that defines a subset possibly of perturbation. If you want simply to do one perturbation, it is possible. Usually you will do all perturbation, moving all atoms in all 3 directions. This is RF_PERT, gives lower and upper bound for I_PERT, and RF_dir, 3 integers that might be 0 or 1 to indicate whether the corresponding I_dir must be considered. Still, not all of these perturbations are equivalent, but some are symmetry related. And ABINIT can identify whether you have already computed a similar, symmetric perturbation, so there is no loss of information from one run to the other. Okay, you will also encounter the fact that in the tutorial we are using the flow capability, internal flow capability of ABINIT with the input variable NDT set, number of data set. How is it managed? I will take the example of a convergence study on the ECUT value. Input variables are by default valid for all datasets. So if I specify ECUT 10, by default, all datasets will have to use 10. But if appended with a number, then it's valid only for that dataset. ECUT 1 will use 10 for that dataset. If I had put ECUT 1 5 and ECUT 1 5 yes, and ECUT 10, then the first dataset would have used 5 and the other dataset would have used 10. Both can be present. The specific value supersedes the generic value for that particular dataset. Then series can be defined with meta characters. This double dot is used to initialize the series, and a plus is used to increment the series. You see, ECUT double dot 10, ECUT plus 2 is equivalent to ECUT 1 10, ECUT 2 12, ECUT 3 14, ECUT 4 16. So you see how one can make a convergence study very quickly. Of course, one can chain calculations. The output of one dataset can be input of the next dataset. This is done at the level of the wave functions. Get wave function for the dataset 2 by looking at the result of the previous dataset, -1. Now, the flow for phonons is really more complicated than such flows, and we can have even double loops with these keywords, NDT set, number of data set, and then UDT set, I don't remember why it was labeled like this, it gives the maximum indices of an inner and an outer loop. And then a meta character question mark indicate the full validity of one of the indices for the different quantities. Let me give an example. NDT set 6, UDT set 3 and 2, so it's a double loop from 1 to 3 and from 1 to 2. ECUT 1 question mark 10, ECUT 2 question mark 15, ECUT 3 question mark 20, will mean that when you have a data set starting with 1, it will use the ECUT 10, starting with 2, it will use 15, and starting with 3, 20. updriver that will tell whether I'm doing ground state calculation or phonon calculation might use the reverse. You see the question mark is now in the first position, and the 1 here refers to the second loop, the 2 here. 1 is 0, and the 2 is 1. This is equivalent to this. You see I'm doing with ECAD 10 these two calculations, but here I change ground state DFPT. Then with 15, ground state DFPT. With 20, ground state DFPT. Okay, it's not very difficult to understand, but okay, I find it quite powerful, but it has nothing to do with the power of Python script I recognize. Now, I can give you the file naming convention. The root name that was mentioned in the files file, the file name file, starts the designation of some results or some output. Then you have here underscore ds for data set, and then the number of the data set. Then underscore, and then you find the final indication of what is this file about. It's a derivative database, the one that contains the second order derivative of eigenenergy, for example. Then there is also the case where first order wave functions or first order density will come as a result of many different perturbations. And they are indicated by an index mentioned at the end of this label. First order wave function for perturbation 12. Okay, so you don't need to master this thing, but when you will read this in the tutorial, you should be aware of what is it about. How much time do I have now? I had 1 hour 15, so 10 minutes ago. 15? Oh, good. Okay, then I will show you some recent thing that has been done with ABINIT that you might even benefit without using ABINIT at all. Electron-Phonon band structure from the Materials Project website. Some of you might already have logged on this website, https://materialsproject.org. It's a big database of computed properties of materials in which many inorganic compounds they have an ID from the ICSD database, so the Cambridge database for structure determination, if I'm not mistaken. And this is the portal of this materials project that also shows some database statistics. The number of inorganic compounds is 69,640. Well, for these, a significant part of these, they have band structure. 53,648 band structure, DFT band structure are available. As an example, I've taken magnesium beryllium nitride 2. This is the idea in the ICSD database. And indeed, you will find after the simple presentation of the crystallographic, this view, that on the material project site can be shuffled around. You will find the electronic structure here with the density of states. And nowadays, there is also for more than 1,000. It's not the 53,000, but still a very large number of materials, phonon band structures that have been obtained thanks to ABINIT. It is not yet seen by the ordinary person, but if you simply click on this link, you will be given access to these. And the phonon band structure for this material, strange material, is actually available there. And there are some nice capabilities also. Where is my... let's hope it will work. Yes, because it's online. I have typed iron sulfide here. I make the search. Yes, so these are all the iron sulfide polymorphs that are present in the materials project database. And I can click on the lowest energy one. So one gets this representation of the iron sulfide structure. The band structure, it's not the one obtained with ABINIT, it was obtained with VASP, actually. But, oh, sorry. I was expecting to have the, perhaps. Okay, perhaps I've been locked out from this. Okay, sorry for the demonstration. In principle, I should have had the That is this one. Yes. This one, I'm sure that we have the Phonon band structure, but it doesn't appear. Yes, okay, this one, it appears correctly. So, so not only there is the band structure, but there is also an interactive band structure. I will repeat this 3 times 3, sorry, times 3 update. Yes, and I will select this phonon, for example, and so you have the thing that starts to oscillate. So you can indeed look at all the different type of phonon in this database. Okay. Let me then finish my presentation. Yeah, it is possible. Oh, it is possible to take advantage of DDB files that are available on this material project, because indeed you can actually download the ABINIT database by clicking here, and then you can do additional analysis, like obtaining the specific heat and other cool properties from the interatomic force constant, etc. It's a good question, because I don't know the answer, and I was wondering this morning, oh, how shall I know exactly what are these 1,500 compounds? I should ask to the Guido Petretto, who is the main key player there. Yeah. But if you try simple solids, and another thing that I have to mention, it's only insulating materials at present that we have, for which we have provided the phonon band structure, not metals. Yes, semiconductors as well. Yes. So, of course, if you type silicon, let's try. Home. Silicon. Electronic band structure, phonon band structure. You have it. Another type of oxide, aluminum oxide, Al2O3. Yes, Okay. So there are many, but it's difficult to know which one, except that the simplest one should be there. Insulator of semiconductors. So you can perfectly take advantage of this without doing any ABINIT calculation. And in particular, in this part of the Jupyter Notebook tutorial, this is a whole set of things that you can visualize from the derivative database. The scripts are provided. Yes, like these. You might wonder how to install ABINIT plus Python plus NetCDF, etc. Just as a side comment, we have developed for those who know an Anaconda channel. It's better than pip install, actually, because precompiled executable and libraries, including NetCDF, will come immediately. So this is the global view on what I have presented. And so today, I just mentioned it very quickly before stopping so that you are not lost. We will suggest you to do a set of common commands. Use the Scratch, for example. Then create, copy to the right place the ABINIT package as well as, some part of the ABINIT package as well as the script. Copy the executable and also make them available directly in your path, which will be more simpler than this. Then we suggest that you go to the ABINIT documentation, and then either you will follow the conventional track, or, and this is a bit more difficult, you will go to the ABI tutorial track. Well, the first part is not difficult because it's completely static. You simply look at HTML file and that's fine. But then either you're working with your own PC and look at the static thing, or you might be brave and install ABINIT on your own PC. But something that we would not like you to do is if you have your own PC, unfortunately, in order to do the tutorial of ABINIT, you would have first to install ABINIT, and so following the conventional track will not be possible, okay? Because except if you are happy to follow the ABINIT tutorial track in which there is installation on your own PC, we will spend a lot of time, well, let's say, we are not sure whether you can do it or not, but I guess most of you will use the local infrastructure and follow the conventional track. Only people, Pythonista, might decide to go straight to the ABINIT tutorial path. Okay, thank you for your attention.